Good afternoon. My name is GRIGORAFT Cosmin, and alongside with my colleagues Valentin, ZICHIL, Elena, NECHITA, Cristina, *BUZOIANU, and Brîndușa, AMALANCEI, we have developed a new system for laboratory-based experiments in technical education, which we consider that is an innovative approach during this COVID-19 pandemic. So the purpose of the paper is to propose a methodology that can guarantee student access to command and operate the laboratory equipment with specific to a technical discipline, which requires practical activities in the laboratories in order for the student to acquire the necessary skills and competencies. So the experimental laboratory stands in technical education are not provided with automatic system for gripping, fixing specimens, and so on, and does not even have an automatic system for varying the loads. These tasks represent, together with taking and processing of the test results, the very matter of the student. So the automation of the stand for bending a rectangular section beam was done throughout software written in Python and C++, and was transmitted to the students using the Microsoft Teams platform. Through the same platform, students can observe the influence of the variation of the load, can read the results regarding the measured values. For this to happen, the complex environment was developed so that distinct libraries like OpenCV, Matplotlib, numerical Python, and PySerial could run together. The most important side of this complex environment is that the experimental setup can be rearranged so other laboratory papers like beam torsions and the buckling can be covered. And also it can be used in face-to-face classes. The custom software includes a 3-camera live feed system along with the experimental stand. The 3-camera live feed system consists of using 2 Android smartphones with the laptop camera in order to visualize the experimental stand and also the teacher explaining. One device, the one that's over here, you can see that it's wirelessly connected. It has no cables, while the one that shows the top view, we can see that it's wired directly to the laptop. So in the middle, the laptop camera is used in this explainer video to show how the other cameras are positioned and also the experimental stand, but regularly it shows the professor explaining. So we can see in the upper left part of the screen the side view is displayed. Over the video feed, a red line is placed to visualize and later on compare the initial shape of the beam. So the top view shows the full extent of the experimental plane, and we can see it in the right side of the screen. So the displacement reading is done using an ultrasonic sensor, which is placed underneath the beam. Okay, this ultrasonic sensor is wired to an Arduino Mega board. The sensor emits and reads ultrasounds similar to echolocation system. It calculates what distance the sound wave traveled in the amount of time. So the system is initially calibrated to 0, as we can see from the live feed. Any deviation of the beam, so like something like this, results in new readings. FreeCAD software, 2 particular actions take place simultaneously. A 3D replica of the beam is deformed as the real one, and also the beam diagram is plotted. In the beam diagram, the shear force and bending moment figures are plotted in real time. Also, the necessary calculations are made and they are displayed in the lower part of the window. So this is the student dialogue module where the student can insert custom values and make the necessary calculations and also generate the beam diagram. So let's say, for example, we want a load of 20 newtons with the length of the beam of 1000 millimeters, the width of the beam 40 millimeters with 10 millimeters thickness. Let's make it a steel, so 210 gigapascals. It's sufficient with a distance between the supports of, let's say, 500 millimeters. We press the generate diagram and also the necessary calculations. So we see that the system has made the shear force diagram and bending moment diagram along with the necessary calculations. From here we take the maximum displacement, which is highlighted over here. It's 0.223 millimeters in this case. So let's say, for example, that we don't want steel anymore, or we want to work with an aluminium. We just insert the Young's modulus of the aluminium there, regenerate everything. So we can see here that it made all the necessary calculations, and also the old diagram is being saved just for the student to compare the values. Our methodology solves the lack of physical interaction between the student and the test stand. In this way, all the tasks of the student were transferred from the physical space to the virtual one. Therefore, we consider that this approach is an innovative way to conduct laboratory classes during the COVID-19 pandemic.